Right, welcome. And we're going to, as I say, do this lesson today on organic reactions. And what we're going to look at today in detail is just 7 tips to help you remember the reactions more easily. So it's not just a mass of things to learn off by heart. It actually will hopefully make sense, why this reaction works and that one doesn't, and so on. So ignore this enantiomers. I didn't mean to have that in. Okay, so we're going to start with the 7 tips. Okay. Oh, and before we do that, this I would like you to do yourself sometime. Just while I'm talking, I'll just let it start up. Because you don't have the organic reactions at home. Sorry, I'm going to, yeah. I'm going to take it through to about here. So you can see here they're mixing the different substances, and can you see there are 2 layers over there, and these are totally dissolved. So have a look, Frankly Chemistry Aliphatic Test. He explains it and he does the whole thing, but I'm not going to go further. Sorry, because he's talking, I can't think myself trying to talk over him talking. Okay, so it's good if you watch that one. As I say, it's Frankly Chemistry. He's got some lovely little organic experiments, and I know a constant refrain from the examiners is say they can see which students haven't carried out any organic practical work. It comes through very clearly. Now, unfortunately, the Te Kura students can't do the practical work, so it's important that you at least watch the video clips. So you'll hopefully remember that this one didn't dissolve, and this is what 2 layers look like. Okay, right, so the first of the 7 tips, and the first one is organic reactions are slow because you have to break covalent bonds, and covalent bonds are strong from your level 2 chemistry, so you're going to need lots of energy to break it. Okay. Ionic reactions are quick. Now you'll say, oh, ionic bonds are strong too. Why? What's the difference? It's the reason is because we put ionic substances into solution, water or some sort of solution, so they are already separated from each other. So the ionic bonds are already broken. So we've already got our separated ions all ready to react. So if I, for instance, just pour some sodium sulfate into a barium chloride solution, I'm going to get an instantaneous white precipitate of barium sulfate, because the barium ions are sitting there already and the sulfate ions are coming in already by themselves. So the moment they come together, there's no ionic bond to break. It can just work. With covalent, that doesn't happen. So with organic, you've got to break those covalent bonds. Now, also from level 1 and level 2 chemistry, how can you make a reaction go faster? A catalyst. Okay, and we do add lots of catalysts in organic reactions. You'll see that come up again and again, so that's good. What else can we do to make a reaction go faster? The concentration, yep. Now, because organic substances tend to be a liquid, we can't really affect the concentration very much unless we dissolve it in something else. And then, yes, concentration plays a part. But heat. So you will find, as I've said here, heating is normally required. So particularly when you're trying to describe an experiment, and you're going for excellence and they're asking you, what you would do and so on, normally heating it is a good idea. Okay, so that's the first tip, that you're going to need heat. And the way we normally heat it is either through a water bath or through a heating mantle. We'll see some from YouTube clips what I mean by the heating mantles and so on. The reason being is organic substances generally, unless they're halo compounds, generally burn easily. I mean, I think you know that from petrol and so on. Ethanol burns, so they tend to burn easily. Now, burning, if something burns, you can say it's inflammable or flammable. Those two words actually mean the same thing. So I know a lot of students think, oh, flammable means it burns, so inflammable means it doesn't burn, and then they'll say, you know, the opposite, or something like that. So, but remember, inflammable means it burns. So if you see inflammable as a label on a product, it means that it's going to burn. Non-flammable is the opposite of inflammable or flammable. So because organic compounds tend to burn, you don't really want Bunsen burners around, and that's why we have the heating mantles. If we have a water bath, it tends to be, you know, at least you've got the water there. If something spills, that it won't, you know, it'll just get dissolved in the water and therefore won't burn as much. Okay, and then of course, if we heat from the bottom or so on, we don't just want all the heat to be around the edges, we want it also to be hot in the middle. And so we have things like what we call magnetic stirrer bars or anti-bumping granules. Because I don't know if you've heated with your spirit burners in the boxes that you get. I don't know if you've noticed that the bubbles, it starts boiling from the outside where it's hottest first and not from the middle. And organic compounds, because they're normally a high vapor or low boiling point, they can sometimes just go shunk and just boil all at once. So that's what we have, these anti-bumping granules. And again, in videos that I'm going to ask you to watch, help shows that. So either you just want something to mix the mixture up, or mix the organic, or just make the organic reactants move around so that the heating is distributed evenly. Okay, now there's two setups that you have to know. Oh, by the way, hi Joe, so you know. There are two setups you have to know. And this is what we call the distillation setup. And we use distillation when we want to isolate a pure compound. Because organic reactions actually are fairly mucky reactions. You can get a variety of products. So what you would do is you'd heat it, and this is an example of a heating mantle I was talking about. We have a round bottom flask in here with our substance, and as it heats, it boils and the vapor goes up, but the lower boiling fractions are going to boil first. So as they go up, the vapor comes in here, it goes through a condenser, and as it goes through the condenser, it starts cooling down and becomes a liquid, and then it drops as a liquid down into a receiving flask. Okay, this bit over here is just to make sure that water doesn't get in, water vapor, because some solutions, you know, water vapor will affect it. And the way you know what fraction you're getting, so what this liquid is here, is by looking at the boiling point. So if it boils at, say, 79 degrees, you know that the ethanol is coming over. But if it's boiling at a lower temperature, it may be an aldehyde that's coming over. Okay, so that is what we call the distillation setup. And you'll notice that this heating mantle also has a magnetic plate that's a magnetic plate in here turns round and round and round inside, which will make a magnetic little magnet that you put inside here to spin around, and it just stirs everything up. Okay, so any questions in terms of a setup for a distillation? There is normally every year a question of either the distillation or a reflux. Okay, so you know you have to get to know this. And I suggest perhaps sketching out, okay, where do you put the substance? In this flask. So what happens is, before you connect everything together and snap it with these green things together, you've just got a flask with an open top. Then you'd pour your stuff in there, or you could have, depending on what substances, you have a dropping funnel that goes in here and it drops down, and then you connect everything else up. So we'll look at a few things so it starts making sense. Okay, right, so here's an example of the glassware. Okay, I'm going to just, so I don't talk louder and louder. Okay, so again, these are, and I do want you to look at them in, after this lesson in your own time. You can either take notes and write these down, or you can look at this video later and then take these. So J.H.U. Adams, if you just Google distillation, it's normally helpful, and David Reed is the other one. So you can see this is a bit clearer, and here you can see he's showing how to connect the things together. So while I was talking, I don't know if you noticed him putting the substance in there, and now he's connecting it up. So there you can see he's connecting it up, and it shows you how to connect the water up and everything like that. Okay, so as I say, I really recommend that you watch those two videos in detail, because it explains what he's doing at that time. And when do we use the distillation? It's to purify a substance and to remove a lower boiling product from a reaction mixture. So for example, I talked about ethanol and the aldehyde. Ethanol, because it's got hydrogen bonding, has a higher boiling point. So if I'm converting ethanol to an aldehyde, any aldehyde that forms, I can distill off first. So I've still got my ethanol here in the flask, and my aldehyde is coming off until I've got no more ethanol left over, because it's all reacted. So that is a purpose of using the distillation. Okay, and now you can see these connecting up the heating mantle and plugging it in, and so on and so forth. Right, this is now the other way of setting up the equipment, and this is what we call a reflux. So again, it's David Reed, if you put it into YouTube, reflux. Okay, and this is when you've got a substance that's fairly low boiling, and you want it to heat it. But of course, if you heat it too much, it's just going to vaporize, and then it's going to go into the air and disappear. Okay, and you're going to lose all your reactant. So what we do is we heat it to beyond its boiling point, so it vaporizes, and it goes up, and I'm just going to move it along a bit. Okay, there he's adding the substance. Anyway, let me move it up. Okay, there. So we heat it in here, and it boils, and it goes up here, it cools down in here, and drops back down again. So you can boil this away merrily for 30 minutes or an hour or however long it takes, and it's going to just keep on vaporizing and dropping back again to the other reactant, and vaporizing and dropping back again. And so over time, if you give it enough time, everything would have reacted. So there you can see what's happening. It's boiling away, and there it's vaporizing, condensing up there, and coming back. So that's an example of a reflux connection, and as I say, we do it when we've got a low boiling substance which we need to heat, and we don't want it. So how does that separate? You don't separate. So this is just to make the reaction happen. You're not separating anything off. You're just making sure that your substance doesn't disappear into the air and leave you with nothing, because it's all gone. So it's just, as I say, organic reactions are slow, so you got to heat and you got to wait, and organic reactions can take days even with heating. Otherwise it's normally half an hour to an hour. Most of the ones I've done are around about that. And then when the reaction is finished, then you can do the distillation afterwards. So that's when you separate. So sometimes you separate during the reaction, and sometimes you separate after the reaction. And we'll look at some of those. So Joe, how do you know when you do one or the other? Basically, the one that's done during the reaction is the aldehyde one. And the others, you know, we'll go through the example. They all then heated and then worked up afterwards. Anything that has acid added to it, for instance, has to be neutralized, and so we'll go through all of those things. So okay, so that was the first tip of heating. So we do the distillation and the reflux, and then we have for the second tip also the special glassware. So that's also the distillation and the reflux setup. And then the other one is extracting. So remember I said just now, if you're adding acid to an organic mixture, then you're going to have to neutralize it. And carbonate is normally used to neutralize it. Why would carbonate be a good thing to use when you want to neutralize the acid in a solution? It's basic, yep, but why use carbonate and not sodium hydroxide? What will carbonate do that sodium hydroxide? Okay, it's a solid, but I could also add sodium hydroxide and make CO2. So it fizzes. So you know when it stopped fizzing that it's neutralized. So we don't muck around in organic chemistry with litmus paper and to see if it's neutral. We just simply add the carbonate until it stops fizzing. So now this is what I've got here is a separating funnel. And so if I've, for instance, added sodium carbonate solution, so here I've added it as a solution. So I've got the aqueous sodium carbonate and I've got my organic liquid layer, and they immiscible. So I'm forming two layers there. I don't know if you can see those two layers. And it's using a separating funnel is a way of separating the organic layer from the aqueous layer. And again, as I say, watch this video, listen to the explanation. Because I have seen questions sort of asking, not directly on all what they've done, but why do you add the carbonate? You know, why add the sodium sulfate at the end? That as we go through it, you'll see the sodium sulfate is for drying, to remove the last little bit of water. So you can see there the two layers, and you just open the tap and you just let the lower aqueous layer run down, and you can discard that and you keep your neutralized organic layer. And it goes through the whole thing, and I think these are at 3.2 minutes they dry. Okay, so he's added sodium sulfate there, and when it stops clumping, you'll know it is dry. Okay, so while you're adding sodium sulfate and it's just forming clumps, it means it's absorbing water that's still trapped in that organic liquid, and you keep on adding it until it's dry, and then you filter. Okay, so as I say, I really strongly recommend that you watch these videos. Okay, third tip is identify the type of reaction. So we've done organic reactions are slow, you got to heat. Okay, then there's all that special glassware, separating funnels, distillation equipment, reflux equipment, and so on. This is now the type of reaction, and there's 4 different types you have to know. I suppose 5, including acid base. One is addition. Addition happens when you have unsaturation. So remember I spoke about those formulae to show if something is saturated or unsaturated. So if an atom is bonded to one less atom than it could be, so in an alkene it's a double bond, so each carbon here is bonded to only 3 other atoms instead of 4. It means you can add one more atom to that, or one more thing to that atom. So carbon could take on another. You can add on. So that's an addition reaction. Okay, so those can add on to those two red carbons. Can't add on to here, of course, because this carbon is saturated. It's already got its 4 bonds. Carbonyls can also be added onto, but you don't really do reactions there. Elimination is the reverse, when you're going from saturated to unsaturated, or even from unsaturated to even more unsaturated. Okay, so an example here is if I've got carbon with a chloride attached to it, then I can remove an atom, the chloride atom, and I can remove either this, a hydrogen from this yellow carbon, or a hydrogen from that yellow carbon. And then if I've removed an atom from each, I don't remove a hydrogen from both of these yellow ones, only from one of them. But can you see if I've removed two groups, the H and the Cl, each carbon is now only bonded to 3 others, so it becomes unsaturated. And we'll be going through examples. The third type of reaction is substitution. And this one I think is the easiest, is when I just swap a group to another group. So it stays saturated, okay? Each carbon has got the maximum number of atoms, but it's a substitution if I go from this compound to that one. I've taken away the chloride and I've replaced it with the OH. So that's an example of a substitution. Fourth type is oxidation. Okay, so oxidation and reduction is one type, or is 2 different types. If you've done the 3070 series, you know that oxidation is the loss of electrons and reduction is the gain of electrons. And that still holds for chemistry, for organic chemistry. But organic chemistry is often, we just simplify it by saying, if you've added more oxygens, or if you've removed some hydrogens, then you've oxidized it. Okay, so oxidation is adding oxygen. But of course, that basic stuff of oxidation is loss of electrons still holds, regardless. Okay, so as an example here, I've oxidized this alcohol to the ketone. Can you see the difference is I have removed this black hydrogen and this red hydrogen. I have removed hydrogen, so I have oxidized. So if you want an easy way of knowing whether you've oxidized or reduced, because it can be quite complicated getting oxidation numbers, simply because the oxidation number for this carbon is different to the oxidation number for these carbons. And so you land up with fractions, and you don't want that. Okay, so if you've removed hydrogens, you've oxidized, or if you've added oxygen, you've oxidized. Reduction is the other way around, is if I went from the aldehyde and I reduced it to the alcohol, I've either added hydrogens or I've removed oxygen. Now, when I say removed oxygen, I don't go from there to there and say that's an oxidation. Okay, it's not a replacement like that. Good point, Joe. A lot of reductions are a type of addition. So that's in a way like a sub. We'd first say it's a reduction reaction rather than addition, but in a way it's an addition too. And an oxidation can also be an addition reaction. So oxidation and reduction sort of tend to overlap addition and elimination. And as I say, we'll show you some examples. Like an alkene going to a diol when you oxidize it with permanganate. So you've added to it, so you've lost the double bond. So it is an addition reaction, but it's also an oxidation reaction because you've added the oxygen. And you know it's been a redox reaction because you've oxidized it with permanganate. And hopefully you know from your oxidation reduction chemistry, permanganate, potassium permanganate, acidified potassium permanganate, is that a very strong oxidant or a very strong reductant? You know, that purple stuff that decolorizes? I hope you know it's a very strong oxidant. Yes, well done. Okay, so if you're treating something with permanganate, you're oxidizing it, because permanganate, that's what it's going to do. It's going to oxidize the other thing. And then, as I say, the other reaction is the acid-base, and I have put it on here. And that's going to affect your amines, which are basic, and your carboxylic acids, which are acidic. And we'll look at those and when we do proteins and so on. Okay, so very quick recap of the different types is, so the different tips. Organic reactions are slow, so they need heating. That means they need special glassware. Okay, and working up and so on, it's all, so you need to know that type of glassware. You need to know the type of reaction. And then the fourth one is identifying the reactive site. If I go back, do you notice I went straight to the chlorine? And I said, oh, if we're going to do elimination, I'm going to remove the chlorine. I didn't look at this hydrogen or that hydrogen or, so on. I went straight to what I call the reactive site. So the functional group is always the reactive site. And the only trick with that is sometimes the functional group has got two parts to it. Okay, and so you've got to work out which carbon. So as an example, here's the alkene. The functional group goes across both these carbons, and yes, that's a functional group. That gives it its function, and that determines its reactivity, and that's where we get that order from. Remember when I was saying about naming, I said carboxylic acid trumps alcohols, and alcohols trumps alkenes, and alkenes trumps alkanes. There's that order, and it's all based on that reactivity. Carboxylic acids are more reactive than alcohols, which are more reactive than, etc. Now, going back to the reactive site, is we know that these two carbons will be involved, but sometimes one atom is going to add to this carbon, and sometimes the other atom is going to add to that one. You need to know that. So this is when I say identify the reactive site. If it goes over both, they're both going to be involved, but what you add to each carbon or to each point may depend on what's happening. Okay, right, so say you look for the functional group. The next thing is you work out, is that functional group, and you look for that carbon atom of that functional group, bonded to a more electronegative or a less electronegative atom, because that'll help you decide also what's going to happen. So as an example, and then that makes it electron rich or electron poor. So if I've got a carbon attached to, say, an oxygen, is oxygen more electronegative or less electronegative than carbon? More. So will carbon be rich in electrons, or will it have some of its bonding electrons taken away, and so it's poor in electrons? Right, Joe, you're ahead of me. It's poor in electrons. So that makes it a bit positive. So what sort of things are going to be attracted to that semi-positive carbon? Notice I'm not saying positively charged carbon, because it doesn't carry a full positive charge. So, okay, is it going to attract something negatively? Right, OH minus. It's going to attract something that's negatively charged or something that's rich in electrons. Here's chloride, OH minus, something like that. Okay, so you aren't expected to know electronegativities off by heart, but you should know the trends, and you should know that as we go from left to right along a period, the oxidation, the electronegativity increases. And what I've just done here is chlorine, of course, is in the next row down from the oxygen and the nitrogen. I should actually have put these in order of the period. Okay. Oxygen, I hope you know, is on the other side of nitrogen, and chlorine is actually below. But oxygen is the highest one to the right, so it has the highest number. Hydrogen is high, in that it's in the first row, but of course it's very much to the left-hand side of the periodic table. So it's lower than any of the other ones. Okay, so hydrogen for the common ones, common elements involved in organic chemistry is the lowest one, and all the other ones tend to be higher. And between carbon and hydrogen, there's not very much of a difference in electronegativity. And that's why hydrocarbons and so on we consider to be non-polar for the organic exam. For the CH3.4, there is still a slight difference, so it will be slightly polar still. Okay, so what we've got here, okay, is what's the functional group here? It's just an alkane, just carbons and hydrogens. That's the functional group over here, and there's the functional group over there. Which of those carbons and which of those three is the reactive site going to be the most positive? In the alkane, in the alcohol, or in the carboxylic acid? So think of which carbon is having most of its electrons dragged away from it. Okay, you zoned out. Okay, it's hard when I just keep on talking. I really admire you if you can last the whole hour. So the question was, which carbon in the functional group, so here it's either this carbon and that carbon, here it's this carbon over here, and here it's that carbon over there. Which one is the most positive of those three? The carboxylic. And it's because it's got two oxygens attached to it, each dragging away bonding electrons. So carbon is not having very much luck in retaining its electrons, because there's a strong drag over there and a strong drag over here. So the only supply of electrons is coming from this methyl group over here. Because remember, hydrogen is less electronegative, so it's pushing a bit of electron density through. And here this is symmetrical, so this is going to be non-polar. Here there's a bit of electron density coming through over here, but there's a big drag out to that oxygen. So this one is going to be the most readily attacked, and that's why carboxylic acids are more reactive than alcohols and alkanes. Okay, because there's a bigger separation of charge. Okay, so that's what I've tried to show here. It's sort of negative there, or slightly negative. So this carbon is going to be much more positive than that carbon, and that one's hardly positive. Okay. And so what I'm trying to say here is this word nucleophile. Do you know what phile means? Liking. Okay, so Philip, the name Philip means likes horses. Okay, hydrophilic means likes water. Lipophilic means likes fat. Okay, so it'll dissolve in fats, or hydrophilic means will dissolve in water. So a nucleophile is something that likes a nucleus. And what charge is a nucleus? Positive or negative? Positive. So we've made carbon a bit more positive over here, so nucleophiles are going to attack it. So nucleophile is something that's going to be rich in electrons, or is going to be negative, and it'll be attracted to something that's positive. So what you're going to get is having, so if you're trying to work out what reagent would I have, it's got to be something rich in electrons that's going to attack these. So either negative charge or just lots of lone pairs. Okay, the next thing is, which bond is going to break? Now over here, if I want to do a substitution here, I've got to break a CH bond, which is actually pretty tough to do. That's why alkanes don't do any reactions, because there's no real site for anything to grab onto. This CH bond is actually a very strong bond and needs lots of energy to break, because there's very little polarization there. Here, we've got a CH bond here and a CH bond here. And we've got a CO bond. So which bond is going to break? A CO or a CH? A CO. Okay, this is more separated in charge. So the electrons are really going more towards the oxygen, so it doesn't take much to nudge out that oxygen with the electrons. So this OH will disappear off with these bonding electrons, and the nucleophile will come in on the other side with its supply of electrons. And here it's even more likely. Now, here you've got a double bond, okay, and here you've got a single bond. So it depends, of course, what you've got, but usually what's stronger, a double bond or a single bond? A double. So what bond do you think is going to break? This one over here or the single bond over here? The single. So it tends to be that this will pop out, and so the OH pops out and the nucleophile pops in. Okay, right. So now that we've identified the reactive site, now we've got to see what's going to leave. And we've already dealt a little bit with that, because I said, is the H going to leave, or the OH, or is it the double bond O? So little tips about what is likely to leave. The more neutral the leaving group, the more easily it leaves. The reason being, if I'm trying to kick out something, and it's then very rich in electrons itself, it can attack back and kick out the nucleophile again. Okay? So it means I've got no reaction. Whereas if it's not very rich in electrons, it's not going to go and kick out that other nucleophile again. You know, the more tough guy has gone in, and the other one isn't tough enough to take it back. Okay? So the more neutral, the more easily it gets kicked out, and it can't get back in again. So the more neutral the leaving group is, the more likely it'll be attacked. So it's perhaps not a very good example, but you know, a robber's going to more likely, if he's got a choice between attacking a strong man with some money on him, or a weak little old lady with some money on her, which one is the robber going to go for? He's going to go for the easy target, okay, the one that he can kick, in terms of chemistry, kick out easily. So the little old lady is more likely to be robbed than the strong man. That's what I'm trying to say. It's perhaps not the most PC example, but I hope that idea comes across. So the more neutral the leaving group, the more likely it'll react. And that actually shows you the reactivity. So I've got an example here of this, I hope, is, let's check your functional groups. Do you remember what functional group this is? An amide, correct. And this is the middle one? Not an alcohol, because it's got the double bond O. If it didn't have the double bond O, it would be an alcohol, but it's this carboxylic acid. Great. And this one? The acyl chloride. Good. Okay. So in each of these, you know, we've got this double bond O, so we're not going to kick that out very easily because it's a double bond, which is stronger. Okay. And so what we're going to have here is, remember when it goes out with these electrons as well, because the nucleophile is coming in with its own electrons. So the leaving group leaves with these bonding electrons. So Joe, yes, you'll have to learn the functional groups. That's always the first thing for organic chemistry. So this, if it leaves, is going to come out as NH2 minus. Now, have you heard of such a compound, NH2 minus? No, because it's extremely basic. Okay? Here, it's going to come out as OH minus. Okay? Right. No, because ammonia is NH3, and it does mean that NH2 minus has to find a hydrogen from somewhere. But what it's most probably just going to do is going to say, I'm going to just go and you know, this is more positive. I'm going to go back and add on here again. Okay, so it's quite hard to break unless you have acidic conditions. So that's actually a very good point to make. I'm talking about totally neutral conditions. But if you had acidic conditions, yes, that bond breaks easily because you make ammonia, and ammonia just bubbles off as a gas. Yeah. So if you have it in acidic conditions, it doesn't kick out the nucleophile. But in neutral conditions, the NH2 minus is going to go out you go nucleophile, unless the nucleophile happens to be stronger. Okay. So here it's OH minus. Now, what do you know about OH minus? Hydroxide. It's a strong base, but not ultra strong like this one over here. So again, acidic conditions will help kick it out more easily. Neutral conditions, a little bit harder. And what about this? What is my ion going to be for this leaving group, for my acyl chloride? Neutral, chloride, totally neutral. And that's why your acyl chlorides are just so reactive, because you have them open to air, the water vapor in the air is already going to start the reaction, because the water vapor, the water is a strong enough nucleophile to come in and kick out a chloride, because the chloride is so neutral. Okay, so that's why, you know, when I said in the last lesson, the way you identify it is by adding the acyl chloride to water and it explodes. It's because it's got such a strong leaving group. Well, no. Okay, in organic chemistry, we tend to just hone on that. It will have, it'll come off as HCl gas, but just looking at this, it'll be chloride. And then the chloride, it depends on what else is there, on what sort of conditions you have. But what I'm trying to point out is what the leaving group would be. And chloride is neutral. Now, when you do the 3060 series, when we look at strong acids, strong bases, salts of strong acids and strong bases and so on, it'll also come clearer about what I mean when I say it's neutral. Sodium chloride is a pH of 7. Okay, because chloride comes from the strong acid chloride, hydrochloric acid. So it has a pH of 7. I mean, just the chloride as a salt. Hydrochloric acid, of course, doesn't. Yep, so what would happen is in any organic reaction, you would have its workup. So remember, like we added that sodium carbonate for the fizzing and so on and so forth. So because we're making an acid, if we added water to this, we're making an acid, and that's why we would add the carbonate, and then that's the chloride then forms part of that salt, and you'd form sodium chloride. So as I say, in organic chemistry, we don't worry too much about balanced chemical reactions. It's we leave that for the inorganic chemists. We just focus on the organic molecule and what's coming in, what's going out, and then we do have to work out what the product's going to be in terms of, so that we know what to work up. So we've got to know it's going to be acidic, the product, so we've got to add the carbonate to get rid of that acid. Okay. Right, so you said, Joe, there, but that's a bit I understand. What, the inorganic stuff or the organic? The inorganic, yeah. You'll find when you go through the booklets, there's very few balanced reactions in there. Okay, so basically I'm trying to show what's happening over here. So NH2 minus is very strongly basic, so it's a poor leaving group. It's an excellent nucleophile, but it's a very poor leaving group. Here we get the OH, okay. It is strongly basic, but not as strong as a NH2 minus. And then finally we've got the chloride. Okay. Right. Oh, what I wanted to say is, why doesn't this bond break? I'm looking at this all the time, and why isn't the methyl coming off? So again, think of, if that bond breaks, what is it coming off as? So if I've got the CH3 and it takes the bonding electrons, it is a CH3 minus, isn't it? Methide. Have you ever heard of methide? No. I mean, it's would be ultra basic. Your carbon-carbon bond is incredibly strong. You'd need lots of energy to bust this one. It's much easier, needs much less energy to bust that one because there's a separation of charge here. This is, very strong non-polar bond. And so if I did break it here, it would come off as methide. And that is so strongly basic, it's just going to go straight back on again. You're not going to get any nucleophile that's going to be stronger than that. Okay, so you're not going to break any carbon-carbon bonds. You'll break, though, a carbon bond that's bonded to, say, something that's more electronegative or even less electronegative in certain circumstances. But even a carbon-hydrogen bond is hard to break, a normal carbon-hydrogen bond. Okay, right. So I just made that point about why doesn't the methyl come off, because I find sometimes students, they just guess and they just add something in anyway. So you just got to think of, this is the reactive side, this is what's coming in, and what's coming out. Okay, April, R simply stands for alkyl. So in over here, the actual example I gave, it was methyl. But it could be ethyl, if I was doing it in the general sense. It could be ethyl, it could be propyl, it could be isopropyl, but each case it would be a alkyl group with a negative charge, which is incredibly basic. Okay, so R is just general for alkyl. Right, so number 6, so we've done it needs heating because they're slow, you need the special glassware, you need, I'm forgetting the points myself, you've got to know the type of reaction, you've got to know the reactive site, you need to know the leaving group, and now this is the reaction conditions. I find a lot of students go, I'll add HCl to that and I'll get my product. It's not good enough. You need to say in what else, because is it dilute HCl? Is it concentrated HCl? You must know your reaction conditions, because if you change your reaction conditions, you're going to get a totally different product. Okay, so for example, if I take a primary alcohol. Now remember, we did do primary about 2 lessons back, where it meant that the carbon the OH was attached to was bonded to only one other carbon. Okay, so if we have a primary alcohol and we distill it with an fairly sort of moderate oxidizing agent like dichromate, okay, we'll get the aldehyde. We'll oxidize it to the aldehyde. If I do it under reflux, it's going to get oxidized even further and go to the carboxylic acid. So if you just simply said, take this propanol and I add some acidified dichromate, I'm going to get the aldehyde. You'll be marked wrong because you could have got the carboxylic acid because you haven't given enough detail. You haven't said that it's distillation for the aldehyde. Because if you just add dichromate, you could get the carboxylic acid too. Okay, so you've got to focus on exactly what else is written with the reaction conditions. Don't just focus on the chemicals, also on what else is there. Another example is, do you add it in aqueous or do you add it in alcoholic? By alcoholic, it means we're using alcohol as the solvent and not water as the solvent. It's not that the stuff's going around hiccuping away. Okay. Right, then the last one is major and minor products. Now, April, I think it was you that said you hadn't done level 2, so you wouldn't have come across Zaitsev's rule or Markovnikov's rule yet. Oh, Joe, Okay. Was it both of you then? Okay, both of you, right. So you're going to learn the Zaitsev's rule and the Markovnikov's rule, because they will help tell you what's going to be a major product and what's a minor product. So you can't just say, oh, if I add aqueous potassium hydroxide, sorry, alcoholic potassium hydroxide and heat it, I'm going to get this alkene. You could get two different types of alkenes. Okay. The shorthand version for Markovnikov is the rich gets richer, but please, that's shorthand, your own little memory aid. Don't write it in the exam, okay? Because it means nothing in terms of, you have to say, so as an example here, Markovnikov applies to addition reactions. With these reaction conditions, do you notice I don't just say sulfuric acid, it's conc sulfuric acid. Now, I know you say I'm adding water and then conc sulfuric acid, why don't I just say dilute? But you do it in 2 steps, that's where it comes from. Okay, I can get, I'm adding an OH, so I've got 2 different carbons there. Now, according to Markovnikov, the rich gets richer, and the full definition is the hydrogen. Yeah, so April, conc means concentrated. So we're adding water, and then we're adding concentrated sulfuric acid. So you're saying, well, you know, a lot of students think, well, I've got concentrated sulfuric acid in water, which means I've diluted it. Why don't we just say dilute sulfuric acid? And I say, no, you have to have it in 2 stages. You have the water first, and then you add the conc. Okay. And actually, you're saying that, Joe, I think it's actually the conc first. It's been a while since I've done this reaction myself, and this is actually this is why you won't ever be expected to discuss why, you know, in which order you do it, but just know that those are your reaction conditions. Now I hope you can see I've got a carbon attached to this carbon that has 2 hydrogens on it, and I've got this red carbon with only 1 hydrogen. So which has got more hydrogen atoms, the blue carbon or the red carbon? The blue. Okay, so when I say the rich gets richer, it's going to add to the carbon that has the most number of hydrogens. I use the pronoun there, it. The hydrogen, the incoming hydrogen, is going to add to the carbon that has the most number of hydrogens. Okay. And the OH, I'm getting confused with my two things. Okay, let's start again here. I've got 2 carbons there, and I've got 2 over here. This carbon only has 1 hydrogen. This carbon has only got 2. Has got, not only. This one has 2 hydrogens. That one has 1 hydrogen. Okay, so for an addition reaction, I'm getting myself confused between addition and the other one, is the hydrogen goes to the carbon of the double bond that has the most number of hydrogens. That's why the incoming hydrogen goes to this yellow carbon, because it had 2, and now it's getting 3 in total. And my nucleophile in here, my OH, goes onto the red carbon. So that's a major product, and a little bit does go to the yellow carbon for the OH, but not very much, and that's the minor product. So that's the Markovnikov's rule. Zaitsev is the opposite. Now there's different spellings, by the way, for Markovnikov. I've seen it with F's, and I've seen Zaitsev with an S, you know, S-A-Y, and it's just simply because these were both Russians. The Russian alphabet is different, and it depends when if the translation came from like the German side or the whatever, because a German S is like a Z. So I suppose the more anglicized version is for the Z, Zaitsev, doesn't really matter. And what happens here, so I'm still using conc sulfuric acid but heating, and I'm forming an alkene. So here I've got a carbon with an OH attached. The carbons on both sides have got different numbers of hydrogens. So what will happen? The carbon with the least number of hydrogens gets any hydrogens it's got removed. So this one's got less than that one, so the double bond forms between the red and the blue. This is a secondary alcohol. You're quite correct, Joe. Primary alcohol, there's only one way it's going to eliminate. Okay, but a secondary can go both ways. Okay, so that's the major and that'll be the minor. And you'll practice that as we go. So those are the 7 tips. Okay, and as I say, did you notice the reaction conditions? So whenever you learn a reaction, have a look at that. Okay, so here, and I'm not going to play these very much, but for the alkanes, all that really is there is that it burns. Okay, alkanes burn. So here there's methane trapped under the ice, so they're lighting up the ice and it's burning away like anything. And they're going to have a nice big fireball over there. Okay, the other one that you'd learn at level 2 is under UV light, you can make alkanes react with chlorine gas, and then you form a haloalkane. Right, the alkenes have got a lot more reactions because they've got that double bond. So these are the reactions you have to know. There are 4 major reactions and 2 tests to learn. And this is what I say is learn a reaction a week or learn a reaction every couple of days because it's a lot to remember. So the 2 tests is if I think I've got an alkene, I can warm it up with some acidified permanganate. If the purple permanganate color disappears, and because of the reaction, it means I form a diol. It means I had an alkene to start off with. That won't work if I just had a plain alkane. The other test is if I add bromine water to this, the brownish or yellowish or color of the bromine disappears because a haloalkane is colorless. Okay, so that's colorless, that's colorless. The bromine I add is sort of a brownish yellow, and as it reacts and adds on, that color will fade. So those are 2 tests you have to know. And then these are both addition, so you would need to know Markovnikov's rule for these when you're trying to work out the product. Here I'm just adding hydrogen to both, so both are getting a hydrogen, so Markovnikov doesn't come in because you're going to get hydrogen added to each one. Okay. So I call this the 4H reactions. Try and say it very fast. Hydrogenation, halogenation, hydration, hydrohalogenation. So you can practice saying that and see how your tongue twisting is. So it's the 4H reactions. Okay, and then as I say, this will go up. So remember I talked about the tests. So there it shows you with the colors. And if I move this a bit on so you see the permanganate. Now they didn't acidify this permanganate, so I'm trying to get it on. So over there. Okay, so there the alkane is not changing color. Okay, and you'll see it's changing color over there. And notice here the alkane didn't change the permanganate. And then I didn't go colorless like you would have expected. And that's because it's not acidified. So instead of forming the Mn2 plus ion, you form the MnO2. You form manganese dioxide. So, okay. So very quick question and then we'll stop. What is added to each carbon of the double bond? Let's see if you've remembered that slide. Okay, halogenation. Okay, it's not as bad because halogenation, I've added halogens. So what's added to each carbon of the double bond? Br. So it's not so bad. Okay, hydrogenation. What's added to each carbon of the double bond? H. Okay, so those are easy. The permanganate test. So permanganate is an oxidizing agent. So remember what I said about oxidation? It's an alcohol. It's adding oxygen or removing hydrogen. Okay, so what am I going to form then? I'm going to just do this. Okay, well, it's actually an OH. Now, I haven't got it here, and I've gone a little bit faster. Hydration. Hydration, you think of water. So you're adding an OH and an H, because that's water, isn't it? HOH. So to one carbon we'll add the H, and to the other one will be the OH. And by Markovnikov's rule, this carbon of the double bond has got more hydrogens than that one, so the H is going to come in here, and the OH is going to go there. And the last one is hydrohalogenation. What are my two things I'm going to add on? H and Cl. Okay, so, and again, from Markovnikov, the H is going to go into the carbon that's got the most number of hydrogens. So there you go. Okay, it is 4 o'clock. And so we'll stop there and go on with... There's lots to remember and go over now in this lesson. Right, bye.